This is video 3.1.2, and our goal here is to understand what E is and how to use it. So hopefully you've read the article on E. The major thing that I saw coming out from your forum discussion was that you didn't know what E was, or where is this number, who invented it. No one invented it, but someone definitely discovered it. And what they realized is that when they performed this operation over and over again, when n got larger and larger, they noticed that the value leveled off. And that's actually the definition of E, is when n gets exceedingly large, that value stays at a constant. It has somewhat of a ceiling to it. So on the right here in the black, you'll see a table. As we plug in values of n, you see that it's getting bigger, logically, because we're taking it to a higher power. It should get bigger, because every time we plug in a bigger n, we're going to a higher power. But what you really notice is that the value starts to level off. Notice how similar 100,000 is to 1 million. Those are very different numbers, but the value here is the same to 4 decimal places. And what they notice is when you went past 1 million, this seems to be the ceiling of the value, that it only goes as high as that. So we only get up to 2.718288183 when we do this value when n is extremely large. And so someone noticed that and said, wow, this is an interesting thing. How can we use this to help us model other real-life situations? So you're going to see how E is used to model things like population, compounding interest, among other things that might be growing, but would probably have a ceiling to them, a place where they wouldn't get much larger than that. So let's take a look at the first one of the major applications, which is interest. When we're compounding interest, we're talking about taking interest money and helping it grow by a certain percentage. Most of you probably have savings accounts or some sort of account, or maybe you already have credit cards. That's also compounded continuously, monthly, quarterly, depending on the account. And it's important for you to understand how your money is growing in a bank account. And this will describe it at n compounds per year. So they're saying that I want to add money to my account n times per year through interest. Okay, so here's some of the things that the variables represent. For both of these equations, P is the principal. Principal is the amount of money that you start with. Okay, so when you put money into a bank account, it's how much you start with. Principal is the word bankers use to describe how much money you originally start your account with. R in this equation, in both equations in fact, R describes the rate. The rate at which you're getting money back. So you've maybe heard things about mortgage rates and interest rates all over the news lately. Rates, we want them to be high when we're saving money, and we want them to be low when we're borrowing money. And so rates are in percentages. What percent of your money are you earning money on? Or what percent are you giving back to the bank when you take out a loan? T represents the time. That's how much time you're going to earn the money over. So are you going to put it in your bank account for 20 years, or are you just going to put it in for 1 year? Usually time is a yearly thing. Different accounts might use time to talk about a monthly thing. The last one that appears in the first equation but not down below here is n. N describes the number of compounds. The number of compounds means how many times are you going to add money to my account while I put it in the bank during that time period. Are you going to add it every five times a year? Are you going to add it just once a year? Continuously? If we continuously adding, that means we're literally always adding money to the account. Then notice we don't use the number n, because that would mean n was infinite, and we know that this value would in turn be E. Okay? And that R actually has an impact on it, which is why R appears down below. So those are the different variables and what they represent. And let's take a look at an example so we can make sense of this. So I'm going to leave these formulas up so we can use them for this problem, this next problem. So here we have a cumulative value of an investment at $15,000 for 2 years at an interest rate of 3.2. If the money is A, compounded semi-annually, quarterly, monthly, continuously. So let's first describe what our variables are. So what does P stand for? Let's see, P in our problem is 15,000 because that's the amount of money I'm initially adding to the account. T is 2. I'm going to save my money for 2 years. My rate is 3.2. I can either write that as 3.2% or 0.032. That's the value without the percent sign, so make sure that you're careful with that. Then for question A, that's where I'm told the number of compounds, the n value. So it looks like for A, my n value is 2. For B, my n value is quarterly, so I'm going to do it 4 times. Remember, semi means twice a year. C, it looks like monthly, so we know there are 12 months in a year. And D, we're continuously, so we're going to use the formula A equals P E R to the T, because n is constantly, it's as many times as we can that year. So let's take a look at what this will mean. So for question A, let's show what we're going to plug into our calculator. So we're going to plug in P times E times 1. Let's see, so P is 15,000 times, so I'm using this formula that you see over here, 1 plus R, so 0.032 over N, in our case is 2, times NT, so to the NT power, so that means I'm going to do N times T, so 2 times 2, or 4. So I'm going to plug this into my calculator and see what it tells me for compounding semi-annually. So the answer for question A, you should be able to plug this whole thing into your calculator as is. The only thing I would do is I would do this math right here and plug in a 4 right there, so you don't have to deal with more parentheses. And you should get an answer of $15,983. Now we do it again, but instead where we put a 2, we're going to put a 4 for this value here. So I'm going to put a 4 in for n and a 4 in for n here. Because now we're going to compound every 4 times a year. So I'll change my values in my calculator and I'll get my new answer, which is a little bit closer to $16,000. And then I'll do it again for C, compounding 12 times. And I'll get a value of 15,990. Wow, it's not much. Wow, it's not much. And last but not least, for continuously. So now for this one, I'm definitely going to be punching in something slightly different. So now I'm going to be punching in for D. I'm going to use this formula. So I'm going to be doing 15,000 times e to the RT. So R is 0.032 times the time, which is 2. So in entering that, we'll see what my best odds are of getting money back. Your E key, by the way, is typically to the left of your 4 key. The letters LN appear on the button, but you can see E to the X in yellow if you have a TI-83 or 84. And you should get a value of 15,991. Okay, so obviously it's better to save more often, continuously get the interest, but notice that it's not a major difference for this particular investment. So your checkpoint problem is going to deal with something similar. Find the accumulated value of a CD of $20,000 for 3 years at an interest rate of 3.1 if the money is compounded continuously. Those are your 4 answer choices there, so you know if you got it correct or not. Give them your best shot, and try using that formula and plugging in what you know. Okay, bring in your questions into class, especially any questions that came up from what you read about E on your computer, on the web page that was directed to you in the